This presentation is delivered by the Stanford Center for Professional Development.
How do we like our Fourier transform so far, class? Yeah. All right. That's the spirit. All right. So let me remind you. Matter of fact, let me reintroduce the star of the show. So let's recall the Fourier transform and its inverse. And I want to make a couple of general remarks before plunging back into specific properties, specific transforms and some properties. And its inverse. So again, f of t is a signal. Then the Fourier transform, or a function, same thing. The Fourier transform, I use this notation. I want to comment about that again in just a second. Integral from minus infinity to infinity of e to the minus 2 pi I st f of t dt. And the inverse Fourier transform looks very similar, except for a change in sign in the exponential. So the inverse Fourier transform of, I'll use a different function, although it doesn't matter. Integral from minus infinity to infinity of e to the plus 2 pi I st g of s ds. Okay? All right, now, I want to make a few general comments here. Simple enough to write down, but it's actually quite a complicated operation. All right, integration is not such a simple operation. Integrating a function against a complex exponential is going to make the thing oscillate. And computing an infinite integral from minus infinity to infinity brings with it all sorts of peril. All right. Now, the rigor police are off duty for the most part. All right, so we are not going to be so concerned about the existence of those integrals. That is an issue, all right, and it is something we're going to have to deal with, but not right away. Right now, I just want to get a little practical hands-on know-how with using the formulas and being comfortable with the formula, so I'm not going to worry about the convergence right now. We will talk a little bit more about it later, although it's never going to be a big issue for us, or rather we're going to talk about it in a number of different ways, all right, but it is something to worry about. So when I write down the definition of the Fourier transform, what I really should have said was the Fourier transform is defined by that integral whenever the integral exists. All right, so the question is the existence of the integral. On the existence of the integral. That is to say, convergence of the integral. Of the integral. All right, so more on this to some extent later. The set of points, but just to introduce a bit of terminology here, something that I'm sure you've said and I actually have used, I think somewhat informally, the set of points for which the integral does exist, that is to say for which the Fourier transform exists, is called the spectrum. All right, so the set of S in R for which the Fourier transform is defined, that is to say for which the integral exists, is called the spectrum. So when I made the bold statement last time that every signal has a spectrum and the signal is determined by a spectrum, I was thinking of exactly this. That is that for, in many cases, the existence of the integral is not an issue. That is, it will exist. All right. In the cases when it doesn't exist, of course, that poses an additional problem. You have to do some further analysis. All right. Now, that's one comment that I wanted to make. As I say, the rigor police are off duty. I'll tell you when we have to worry about those kind of questions. Now, the other thing I wanted to say is that our definition of the Fourier transform and the notation I'm using for the Fourier transform is not universal. Matter of fact, there is no universal definition or universal standard, universal notation for the Fourier transform. So definitions and notations vary. All right, you should be aware of this. And it's not that one is, and no single notation is perfect. All right, different notations are useful in different contexts. So you will see, for example, the notation f hat in really sort of corresponding to what we did for Fourier coefficients. You will see the notation f hat for f hat of s, or what I'm calling for the Fourier transform. You will also see, this is a pretty cute notation, you'll see an upside down hat for the inverse Fourier transform. I'll call it T. All right, you see that notation. It's not uncommon at all. All right, you also see, that's probably the cutest one, but it sort of gets lost in typesetting. You also see a very common notation in engineering, especially, is to use a lowercase letter for the function, for the signal, and an uppercase letter for the Fourier transform. All right, so you also see f of t for the signal, and f of s for the transform. All right. The problem with this notation is that it's not so good when you talk about duality, which we're going to talk about today, actually, because it really makes more of a distinction somehow than there ought to be made. Anyway, but it's useful. All these notations are useful in some context, but no notation is useful in every context. There's always some ambiguity. There's always some clash. All right, and you have to be flexible, and you also have to know which notation the person, the particular author, the reference that you're looking at is employing, because people will use different notations. There's also a notation that people use for the sort of sibling relationship, which will mean more to you in just a second when I talk about duality, between a function and its Fourier transform. So some people write things like f of t corresponds to f of s. I sort of use that notation, but there's this other notation which I think is just idiotic, which is like a subset notation or something like that, right? Like, does it go this way or the other way or something like that? I hate that notation, but it's used. Bracewell uses this. God rest his soul, but it's a stupid notation. I'm sorry. You know, he's dead. It's gone. All right. Finally, maybe it's something like that. Anyway, say no notation is perfect, but some notations are worse than others. Finally, it's not universally agreed on how the Fourier transform itself should be defined. All right? There are different definitions. I think, actually, let me just go back. I think the notation, the script F notation that I'm using, and a lot of other people use also, is the least ambiguous notation. It's sometimes awkward in certain contexts, but it's the least ambiguous, and somehow I tend to gravitate toward that more than others. But again, you know, you can choose what you want, and you'll see them all in use. Anyway, I was going to say there are also different definitions that are in use. For example, one sometimes defines the Fourier transform of, it's where you put the 2 pi and where you put the minus sign. All right, so you will see this definition. You'll see the Fourier transform of f at s is the integral from minus infinity to infinity of e to the I s t f of t dt with no 2 pi up there, or you sometimes use it as I omega t instead of s. All right, and you'll see the inverse Fourier transform, the minus, without the 2 pi. You'll see this notation. You'll see the Fourier transform of f of s is 1 over 2 pi times the integral from minus infinity to infinity of e to the minus I s t f of t dt. Sometimes putting the factor of 1 over 2 pi out front. You will also sometimes see the Fourier transform with a plus sign and the inverse Fourier transform with a minus sign. All right. You'll also see the Fourier transform of f at s is integral from, or sometimes with a 1 over 2 pi out in front. All combinations are in use. All right. E to the plus I s t f of t dt, and the inverse Fourier transform is the integral from minus infinity to infinity of e to the minus I s t f of s ds. All right. You'll see all these notations in use, and you just have to know. Somebody has to tell you, or somehow otherwise you have to figure out which particular convention is in use. All right, this one is actually especially popular in physics. All right, it's quite often in problems in optics, for example, where the Fourier transform comes in. You often see this is the definition of the Fourier transform. Sometimes with the 2 pi in there, you can stick it here, you can stick it there. If you don't like it, you can stick it someplace else. And this is the definition for the inverse Fourier transform. All right, all I can say is be careful out there. In the notes, I moved this in various places. I'm not sure the best place to put this. I think it's now at the end of the chapter called the chapter on convolution, which we'll get to very shortly. There's a section called Chase the Constant or something like that, which I stole from a book by Tom Kerner, and that tells you how the different formulas change when we change the plus sign to a minus sign, when you change where you put the 2 pi and so on. All right, so it's sort of it's meant to serve as a dictionary. To help you translate one case from another case or one convention from another convention when you're likely to run across them, and you will be likely to run across them. Okay, so I felt like I ought to tell you that. Now, I think I may print that out separately and actually just give it to you sort of as a dictionary, so you have that, so you can make that translation, because I say it's just a pain in the neck. What can I say? But it's somehow in the nature of the subject that there's not a universal definition. I think it's fair to say that the convention, the one that I've given there, is probably the most commonly. Even then, I'm a little bit hesitant to say that, but I think it's safe to say it's the most commonly accepted convention, but by no means is it universal. Okay. All right, and we also had last time, so to remind you what we did last time, we had two basic examples of the Fourier transform, calculating the Fourier transform. And again, at this stage, the only way we have to calculate the Fourier transform is by recourse to the definition. You have to carry out the integration if you can. All right? There's no way of getting around it. We'll learn then today and then going on other techniques that will allow us to calculate Fourier transforms, new Fourier transforms from old Fourier transforms. But for now, right at the beginning, there's nothing to do except plug into the formula. So the basic examples we had, which come up often, very often in applications, are the rectangle function, pi of t. That's the function that looks like this. It's 1 from minus a half to a half, and then 0 outside the interval. And I don't care how it's defined at the endpoints, because it doesn't make any difference in the calculation. And the Fourier transform of that is the sinc function. F pi of s is sinc of s, which is, by convention, sine of pi s over pi s. And that's, by the way, of course, another thing that's not universally agreed upon. Some people define the sinc function without the pi in here. Some people just say that it's sine of s over s or sine of x over x without the pi. What are you going to do? What are you going to do? The other example that we had, I didn't carry out the calculation completely, but again, it was based on just calculating the integral. In this case, you had to use integration by parts. It's the triangle function. Has slope 1, going up from minus 1 to 1, and then down from 1 to 1, 0. That's lambda of t, and the Fourier transform there is the sinc squared. Nice result. Sinc squared of s. Okay? All right. I want to do one more particular case that's really cool, actually, and also comes up quite a bit in applications. And then we are going to take the different path, the second path that I talked about. That is, talk about some general properties of the Fourier transform and how you use the Fourier transform to find, how you can formulate some general properties that will allow you to find Fourier transforms of combinations of functions or modifications of functions. But let me do one more explicit example for you, and that is our friend the bell curve, the Gaussian. That's a very important application. That's a very important function in many applications. And it has a remarkable property with regard to the Fourier transform. So as a third example, let me do the basic Gaussian, f of t equals e to the minus pi t squared. Now again, there's a question of normalization here. All right. The shape is the familiar bell-shaped curve, which comes up in probability distributions. And I'll talk about that probably a little bit next time or the time after that when I talk about the central limit theorem. It has a height of 1. And with this normalization, that is putting the pi in the exponent, that normalizes the area under the curve to be 1. It's not the only way of doing it, but it's the way of doing it that's somehow most convenient most natural when you're working with Fourier transforms. So the result, when you make this normalization, is the integral from minus infinity to infinity of e to the minus pi t squared dt is 1. Now, I'm not going to, as tempted as I am, I'm not going to show you why that's true. I'm not going to do the calculation. That's one of the most famous tricks in all of mathematics to get that result, going back to Euler. You cannot do this by direct integration because the function e to the minus pi x squared has no elementary antiderivative. So you can't do this with the fundamental theorem of calculus. It has to be done by a very devious other means. And it's done in the notes. You should look it over. If you have any questions, ask me about it because I never get tired of talking about it because it's such a famous and elegant trick. But in the interest of time, I think I won't go through the derivation. All right, but that's an important result. And a surprising result. I mean, why e pi 1? Why should they all come together in such a simple formula? But they do. So here's what I want to show you. And to let the cat out of the bag, I'll show you where it comes from, is that the Gaussian is itself. No, the Gaussian is itself. I am myself too, and you are yourselves, but that's not so interesting. What's interesting is that the Fourier transform of the Gaussian is itself. That is, if f of t is equal to for this normalization, e to the minus pi t squared, then what I want to show you is the Fourier transform is the same function, e to the minus pi s squared. I'm using a different variable there, but the basic fact is that the Fourier transform of the Gaussian is the Gaussian. Now, I mean, it's a very striking result because computing the Fourier transform is a complicated operation. As I'm going to go through this to show you how it works. So why a function should turn out to be itself under Fourier transforms is really quite striking. We'll also see soon that, you remember, you've heard me talk about many reciprocal relationships between the time domain and the frequency domain. And we're going to see various examples of that. And somehow, what this tends to say is, for reasons which you'll understand a little bit better later, is that somehow the Gaussian is equally spread out in the time and the frequency domain. There's no difference. Because often what happens is, if a function is spread out in one domain, it's stretched out and it's squeezed together in the other domain, or vice versa. All right? That's what we'll see that actually as an example of, well, we'll see that as a basic property of the Fourier transform. And what this says, the fact that the Fourier transform of the Gaussian is itself, means somehow it is equally spread out in both time and frequency. All right? Which is something it wouldn't occur to you to say or occur to you to think about unless you knew this result. All right? So why is something like this true? All right? We have, again, no recourse other than to the definition. So let me write, in this case, I think it's a little bit easier to actually use the capital letter notation because I'm going to be differentiating and performing some other unnatural acts on the Fourier transform. So watch. So let me call, again, if f of t is equal to e to the minus pi t squared, let me call capital F of s its Fourier transform. So that's the integral from minus infinity to infinity, e to the minus 2 pi I st e to the minus pi t squared dt. Okay? And I'm actually going to evaluate this integral. All right? Not by any sort of appeal to the fundamental theorem of calculus or anything like that. That won't work, but there is a clever trick that will actually allow us to carry out the integration after an initial little sleight of hand. That is to say, I'm going to differentiate with respect to s. All right? That is f prime of s, and this can be justified. The rigor police are off duty, but even if they were on duty, I would have no trouble in asserting that I can find the derivative of this function by differentiating under the integral sign. So the integral from minus infinity to infinity, the derivative of this thing is dds. The only thing that depends on s here is this complex exponential, e to the 2 pi I st, and then e to the minus pi t squared stays the same. Doesn't get hit by the derivative. So the derivative of this with respect to s is equal to the integral from minus infinity to infinity of minus 2 pi I t e to the minus 2 pi I st, then e to the minus pi t squared dt. Okay? All right, now, watch this. Let me factor out the minus I. Let me factor out the I, rather. Let me write this as I times the integral from minus infinity to infinity. I want to group terms in a very suggestive way. So it's going to be e to the minus 2 pi I st, and then 2 pi t minus 2 pi t times e to the minus pi t squared dt. And I group the terms this way because it cries out to be integrated by parts. All right? Differentiating with respect to s brings down this factor of 2 pi t, or minus 2 pi t here. All right? This absolutely cries out to be integrated by parts. This is the u. This is the dv. Okay? And if I do that, what happens? Well, if dv, once again, is minus 2 pi t times e to the minus pi t squared dt, then v is e to the minus pi t squared. All right? Derivative of this, e to the minus pi t squared, brings me down with respect to t, brings down the minus 2 pi t. All right? And if u is equal to e to the minus 2 pi I st, then du is equal to minus 2 pi I s e to the minus 2 pi I st, 2 pi I st dt. All right, I'm differentiating there with respect to t, or d'ing with respect to t, so to speak. Okay? All right, so again, integration by parts tells us that the integral from a to b of u dv is uv, evaluated between a and b, minus integral from a to b of v du. All right, so what's that, how does that work out in this case? In this case, I get, there's an I times the whole thing, right? So it's an I times u times v, which is e to the minus pi t squared, that's a v, pi t squared, times e to the minus, where's u? U is minus 2 pi I st, and evaluated between minus infinity and infinity, minus the integral from minus infinity to infinity of v du. V is e to the minus pi t squared, du is minus 2 pi I s e to the minus 2 pi I st dt. All right, close braces here because there's an I in front of the whole thing. Cool? Way cool. All right, now what about these boundary terms here? What about the terms u times v between minus infinity and infinity? What happens to that? Gone! All right, because this thing has absolute value 1. E to the minus pi t squared is going to 0 at both plus and minus infinity. All right, so this is killing this off. It is gone! What remains? What remains is minus 2 pi is, a minus sign here, and then there's an I in front. All right, so if I got all that right, it's going to be an I times an I, and I times an I is a minus 1. Right, so this is going to be, right, there's a minus, and then an I times an I gives you an extra minus 1. It's going to be minus the integral from minus infinity to infinity of 2 pi s times e to the minus 2 pi I st e to the minus pi t squared dt. Okay? Now, I'm integrating with respect to t. This comes out. This depends on s. So this is minus 2 pi s, integral from minus infinity to infinity, of e to the minus 2 pi I st e to the minus pi t squared dt. Brilliant. I've gotten back to where I started. All those years of education, all that work, what did it get me? Back to where I started. Except there's an extra factor out front. That is, this is equal to minus 2 pi s times f of s, the original Fourier transform. That integral is the Fourier transform of the Gaussian. Integral from minus infinity to infinity e to the minus 2 pi I st times e to the minus pi t squared. All right? So what have I shown here? I have f prime of s is equal to minus 2 pi s times f of s. Oh, but that's just a simple differential equation for f. Kids? Right? So that says that f of s is equal to the initial value f of 0 e to the minus pi s squared. That's the only solution to that baby. Okay? And what is f of 0? What is capital F of 0? Capital F of 0 that's the value 0 of the Fourier transform, actually, right? Value when s is equal to 0, so it's minus infinity to infinity, e to the minus 2 pi I 0 times t, e to the minus pi t squared dt. That's the integral from minus infinity to infinity, e to the minus pi t squared dt, which is 1. Okay? So what is the actual retail value of the answer? That says that f of s, capital F of s, is e to the minus pi s squared. This says that capital F of s is e to the minus pi s squared. Done. Fantastic. Fantastic. All right? So again, I take the Fourier transform of the function e to the minus pi t squared. That corresponds to, if I want to use that notation, to pi s squared. All right? The Fourier transform of the Gaussian, when it's normalized this way, is itself If you change the normalization, you're going to get a different answer, although we'll figure out how to do that. We'll figure out how to make such changes. But for this Gaussian, the way it's normalized, e to the minus pi t squared, its Fourier transform is itself. Quite remarkable and quite important. All right, quite important. Okay. All right, now, that's about all I want to do at this stage for specific transforms. I only have three, actually. The rectangle function, the triangle function, and the Gaussian. There are other examples in the book, all right? There are other examples in the notes. There's the one-sided exponential decay, the two-sided exponential decay. I'm not going to go through the calculations, all right? If this were a regular calculus class, I'd go through all those calculations, but you're beyond that. You can read the calculations. You can certainly use the results, all right? They all have to rely on using the definition of the Fourier transform. There's no other recourse. That's all you have to work with is the definition, all right? So that means all you have at your disposal is, well, there are tricks like this, but typically they're just integration techniques. And the integration techniques are usually integration by substitution or integration by parts. That's all that's used in any of those derivations, all right? So I'll let you go through those things and certainly use the formulas. There's no reason to memorize them, especially. I mean, if you can always look them up if you need them. They're there and so on. Instead, what I want to do now is I want to talk about some general properties of the Fourier transform. I mentioned there are two paths that we want to follow. One is finding specific transforms, and then one is finding general properties of the Fourier transform that will allow us to find the Fourier transform of different combinations of functions. So now I want to pursue that second path and look for general properties. And the first one I want to look at often goes under the heading of duality. So I want to explain that to you. It's actually very simple, but Fourier transform duality. All right, the formulas are extremely simple, but for some reason, well, for reasons which I'll explain to you, many times students really agonize over these formulas. All right, so I want to go through it in a little bit of detail. Here, what I want to do is I want to exploit the similarity in the formulas for the Fourier transform and its inverse. That's what this is about. Between the formulas for the Fourier transform and the inverse Fourier transform. Okay? That is, the Fourier transform of, let me write down the definition again. The Fourier transform of f of s is the integral from minus infinity to infinity e to the minus 2 pi I st f of t dt. Okay? Now, remember the Fourier transforms, say this to yourself early and often. The Fourier transform is an operation that turns one function into another function. All right? To evaluate the transform, I have to evaluate it at a variable. In this case, I'm calling the variable s. Fine. That means I plug s into the formula, and that tells me how to compute the Fourier transform. Fine. What if I plug in minus s into the formula? All right, the Fourier transform of f evaluated at minus s. The Fourier transform is an operation that turns a function into another function. To evaluate it, I have to plug in a point. I plug in the point minus s. What do I get? I get the integral from minus infinity to infinity of e to the minus 2 pi I times minus st f of t dt, which is the integral from minus infinity to infinity of e to the plus 2 pi I st f of t dt, which is, if according to my formula for the inverse Fourier transform, the inverse Fourier transform of f at s. Let me write that down one more time. Okay? The Fourier transform of f at minus s is the inverse Fourier transform of f at s. Fine. That's exactly what that formula says. Now, this gives some people just fits. All right? Why? Because this is an example of being wedded to an interpretation. All right? This is an example that is, if it gives you fits, it's because you're too wedded to an interpretation and wedded to your variables. All right? Because they say, how can you take How can it be s on both sides of the equation? If I take the Fourier transform, I get into the frequency domain. If I take the inverse Fourier transform, I get back into the time domain. But you're calling it s in both cases, man. How can you do that? Are you allowed to do that? What kind of fool are you, man? It doesn't make sense, all right? That's because you always think of, or people cling to the idea that they cling to one particular interpretation. You have a signal in the time domain. This Fourier transform is something in the frequency domain. You cannot mix the two in your head or anywhere, ever, all right? And so this formula bothers people. You take the Fourier transform, evaluate it at minus s, the same thing as taking the inverse Fourier transform. But I say to you, as I said before when I was doing it, and that's why I was making the point, the Fourier transform is a formula, is an operation that turns one function into another function. To write down the formula, you have to evaluate the operation at a variable. It doesn't matter what I call the variable. I can call it s, I can call it t, I can call it zippity-doo-dah, I can call it anything, all right, as long as I am consistent. All right, and there's no inconsistency, there is no error in this at all. All right, so don't think in terms of time, frequency, or whatever. Think in terms of the mathematical operation. The Fourier transform evaluated at minus s is the inverse Fourier transform. Now, there is a neater way of writing this. This statement, actually, and related statements, which I'll show you now, are, this is exactly sometimes called duality, or the principle of duality, or duality for Fourier transforms, or whatever. You would have a tough time. This is an example, actually, where you would have a tough time with other notations. All right, if you use the capital letter notation, all right, that would give you fits, because the capital letter notation somehow forces you to distinguish between the two domains, little f of t, capital F of s, you know, and that would make it hard to write down that formula in a way that really made sense, all right? But if you use the operational notation here, or the operator notation, then it's easy to write down, it's unambiguous, and there's no problem with it, all right? Now maybe, like I say, maybe you're looking at me like, what is the problem? I don't have any problem with this, but trust me, I have seen many times, many people have a lot of trouble with that formula because they're trying to interpret it in ways that it can't be interpreted. It's just a mathematical statement, all right? It's a very useful mathematical statement, and as it turns out, but it is a mathematical statement. It's not a statement about time and frequency, not to my knowledge, all right? Now I want to write this another way, write more neatly. I think actually it's also a good idea, I think, to try to write things in as variable a free way as you can, all right? Or try to introduce, even if you have to introduce a little extra notation, to try to not write your variables, because in this subject, writing variables and naming variables just can get things pretty muddled, all right? So I want to write this a little bit more neatly in a way that will actually allow me to write the duality formulas without any variables, where there's sort of no agonizing, or perhaps no agonizing. So I want to introduce the reverse signal. Matter of fact, I think this was even on the first homework, first or second homework, all right? That is, if f of t is a signal, then I define f minus of t just to be f of minus t. All right, not a big deal, all right? So you reverse, if you want to think of t as time, you're reversing time. That's why I call it a reverse signal. Okay? Then, first of all, it's a nice way of expressing evenness and oddness, actually, then, in terms of the reverse signal. F is even if the reverse signal is equal to itself, because to say that f is even is to say that f of minus t is equal to f of t. So to say if you reverse the signal, you get the same signal back again. F is odd if you reverse the signal, you get back minus the signal, because f is odd if f of minus t is minus f of t. All right? So it's a nice, simple, let's say, variable-free way of writing it, if you want. And what does this formula say? What does the duality formula say, the first duality formula say? Once again, with variables, it says the Fourier transform evaluated at minus s is equal to the inverse Fourier transform of f evaluated at s. All right? I want to write this in a variable-free way using the reversed signal. What is the Fourier transform of f evaluated at minus s? It is the reverse of the Fourier transform. Now, watch very carefully where I put the parentheses. This is equal to this, because the Fourier transform of f reversed, evaluated at s, is the Fourier transform of f at minus s. Okay? So this statement in a variable free way says the Fourier transform of f reversed is the inverse Fourier transform of f. Kind of nice. I mean, that's, the reverse, the reverse of the Fourier transform is the inverse Fourier transform. That's why, in fact, some people talk about the forward Fourier transform and the reverse Fourier transform. Actually, they don't even use the term transform and inverse. They sometimes talk about the forward transform and the backwards transform or the reverse transform. And I think what they're often thinking about is this formula, although there's this extra sign change in there. So this is the Fourier transform of f reversed is the inverse Fourier transform of f. Now, what about... So that's one form. I didn't do anything new there. I just rewrote the formula in a variable free way. It's a way that I can tend to remember a little bit more easily, to tell you the truth. Let's look at something else. Let's look at the Fourier transform of f minus, the reverse signal. All right, notice the parentheses there. All right, I'm not reversing the Fourier transform of f. I'm taking the Fourier transform of the reverse of f. What is this? Well, in order to evaluate this, I have to evaluate it at a point. So the Fourier transform of f minus at s is, by definition, the integral from minus infinity to infinity, be careful here, of e to the minus 2 pi I st f reversed, a t, dt. That's by definition of the Fourier transform. The Fourier transform of whatever I plug in here is what I plug into the formula. In this case, it's f minus, f reversed. This is the integral from minus infinity to infinity of e to the minus 2 pi I st f of minus t dt, by definition. All right? Now, I'm going to work with that a little bit. I'm going to work with that last expression. I'm going to make a change of variable. All right, this is just an exercise. This is really an exercise in logic and notation. All right, and I'm only doing it because I can tell you that logic and notation can be a problem in this subject. All right, finding your way through the notation and making sure you're saying the right thing and not saying the wrong thing can be a challenge. I have seen generations of students, very smart students, get exactly balled up over these points. So that's why I'm doing it. And let's hope I can get through it correctly. I'm going to make a change of variable. I'm going to let u equals minus t. All right, that's sort of the obvious thing to do here. If I want to get rid of, I want to get rid of this f of minus t there. So I'm going to make a change of variable in the integral, u equals minus t. So du is equal to minus dt. Okay. So what happens to the integral? The integral from minus infinity to infinity of e to the minus 2 pi I st f of minus t dt becomes, let's do one step at a time, all right? This is the integral of e to the minus 2 pi I st, so t is equal to minus u, so it's minus 2 pi I s minus u, f of u, and dt is minus du, all right? Then you have to change the limits of integration also, all right? So if I let u equals minus t, and if t goes from minus infinity to infinity, then u goes from infinity to minus infinity, all right? So u goes from from plus infinity down to minus infinity. Once again, if t goes from minus infinity to plus infinity, then minus t goes from plus infinity to minus infinity. But so that's the integral e to the 2 pi I su f of u du. And there was an extra minus sign out front, so it's minus the integral from infinity to minus infinity. That switches the limits of integration. That becomes minus the integral from minus infinity to infinity. Okay. What remains, dear friends? What is that integral? We recognize that as the inverse Fourier transform of f evaluated at s. Okay. What is the conclusion? The Fourier transform of the reverse signal is also the inverse Fourier transform. If I don't write the variable in there, all right, the Fourier transform of f reversed is the inverse Fourier transform. All right? That's another duality theorem. Now I want to combine this with the earlier one that I had. Where was the earlier one I had? Was the inverse Fourier transform of f inverse Fourier transform of f, was the Fourier transform of f reversed. That's this one over here. All right? That's the first duality statement that I had. If I combine this one with this one, then I get a very nice statement. I get that the Fourier transform of f reversed is the inverse Fourier transform of f. That's the Fourier transform of f reversed. So just look at this one and this one. This is my favorite statement, actually, of the duality statements, because the easiest one for me to remember. It says that the Fourier transform of the reverse signal is the reversal of the Fourier transform. In words, it's so easy and it's so nice. The Fourier transform of the reverse signal is the reverse of the Fourier transform. All right, that's another statement of duality. All right, there are no inverses in there. I short-circuited it by putting the inverse in the middle. The Fourier transform of f inverse, the Fourier transform of f reversed is the inverse Fourier transform of f. The inverse Fourier transform of f is the Fourier transform of the reverse signal. See, I can say all these words fast enough, because I say everything fast, but I can say all these things because I've been through it a couple times. All right, and because I am not afraid not to write my variables. So you have this statement. That's another statement of duality. So there's this statement. There is the first statement that I had, the Fourier transform of f reversed is the inverse Fourier transform of f. All right? We use this statement to get this statement. There's one other formula. They're all basically the same. There's one other formula that people often lump into sort of duality statements. And that is if you take the Fourier transform of the Fourier transform. Now watch this. This is cute. One more. And that is the Fourier transform of the Fourier transform of f. Okay? Now, you can derive this a number of ways. I think I will only give you the result of this thing and not tell you what and not give a derivation. But the result is, if you take the Fourier transform of the Fourier transform, you get back the reversed. You don't get back the function. You get back the reverse signal. You get back f reversed. Okay, so you can derive this. You derive this. You can derive it as a consequence of what we've already shown over there. You can try to do it from scratch, just with the definition of the integral. Don't worry about convergence or anything like that. Just see what happens if you plug it into the definition. And again, people have a hard time with this because they're wedded to this interpretation of the Fourier transform as taking you from the time domain to the frequency domain. That's not that interpretation is wrong. I mean, in many cases, you want to think in terms of two domains. You want to think in terms of time and frequency, but not always. All right? Not always. Sometimes you just want to think of the Fourier transform as an operator taking one function to another function. I have to plug in a variable in order to write down the formula, but it doesn't matter what I call the variable. It doesn't matter how I interpret the variable. All right? It's just a statement. It's just a mathematical statement of how the thing is defined. All right? So if you think that way, then you have no trouble. It's one thing to derive this formula, but there's certainly no inconsistency here. There's nothing here that shakes your faith in the world, all right, or shakes your faith in the distinction between the time domain and the frequency domain. You know, screw that. Excuse me. All right, it's just a mathematical statement. Now, these are very useful. All right, these come up a fair amount, and I'll give you one example. I'll give you a quick application. All right, quick application. There's an application of this to actually finding Fourier transforms. All right. So, for example, let's find the Fourier transform of the sinc function. All right. We found the Fourier transform of the rectangle function is equal to the sinc function. We haven't found the Fourier transform of the sinc function. So we know. I'll do it over here. Now I do this actually one way in the notes. Let me do it a slightly different way here. All right. We know that the Fourier transform of the rectangle function is the sinc function. All right. So the Fourier transform of the sinc function is the Fourier transform of the Fourier transform of the rectangle function. Right? Fourier transform of the rect. That's the first calculation we did. Fourier transform of the rect function is the sinc function. Fourier transform of the sinc function is the Fourier transform of the Fourier transform of the rect function. But the Fourier transform of the Fourier transform of the rect function is, according to this formula, the reversal of the rect function. But the rect function is even. All right? The rectangle function is an even function. So this is the rect function again. lightning fast, we have derived that formula. Now, you would be hard pressed, all right, to show. Let me just indicate here what the issue is. If I were to say to you, find the Fourier transform of the sinc function, and you were to say to me, I have only one recourse, and that is to the definition, all right, you would have to write down the Fourier transform of the sinc function at S is the integral from minus infinity to infinity e to the minus 2 pi I st sine of pi s divided by pi s, sine of pi t divided by pi t dt. Good luck. Right? Good luck. There are real serious issues of convergence here for this integral. I mean, and trying to evaluate this, and imagine that this evaluates to, if we believe this, the function which is 1 from minus a half to a half and 0 elsewhere, and really? No? Oh, kidding? All right? You would be hard pressed. But the duality makes it easy. All right? Now, like I said, this works because the rigor police are off duty. All right? This works because I'm assuming that there's actually no problem with the definitions, with the formulas and so on, that all the integrals work and so on. It takes a lot of, actually takes some work to do this. All right? It takes some work to, I mean, it is true, this statement is true, that the Fourier transform of the sinc function is the rectangle function. But actually to do that completely rigorously requires a certain amount of effort, which we're not going to do, actually. I mean, we're going to do it, but by sort of by indirection. But nevertheless, with the rigor police off duty, and it's okay, you find very simply how it works. And you find a very similar, the same sort of argument will give you that the Fourier transform of sinc squared is the triangle function. Same duality argument. Same duality argument gives that the Fourier transform of sinc squared is the triangle function. Okay? Same thing. All right, I tell you what, I usually keep you overtime. I think today, maybe we'll even get out on time. God forbid we get out early. Next time, what I want to do is I want to continue the discussion of general properties. I want to talk about the so-called stretch theorem, the shift theorem, and talk about convolution next time. So I want to move ahead a little bit and make a little bit push to get some of the more general properties of this. Okay? See ya on Wednesday.